Okay, let's start with page 12. Okay, so the graph consists of line segments. Let g of x equals the integral from 2 to x of f of t dt. So first, it says find g prime. So we want to build our derivative, second derivative, based off of this. We know that this right now g is defined as something above f, which means that we're going to have to find the area under the f to do anything that's g related. So if I want to find g prime, I gotta find the derivative of this, right? Which is going to bring this down one level. So second theorem, we know derivative and integral will cancel each other out. And we just have to plug the upper bound in for the x. So hopefully we see that relationship, right? That if we're sitting one level above f, then the derivative will bring us down to where f is. Yeah.
Just write F.
Yeah, you can. I just want to show you why that's happening, but yeah, you can just go from here to here and not or show that step. Okay, next up, g double prime. We're just going another derivative level down, so f will take us down to f prime. Okay, next up, part C, find g of 4. So if I want to find g of 4, I'm just going to identify the fact that I need to work with that g of x function. So we're just going to plug 4 in for x and do what the definition tells us. Accumulate the area under the f graph between 2 and 4. Okay, so I'm looking at this thinking about, do I have to worry about changing the bounds? Are the bounds okay? And it should be okay, right? We're starting small, going larger. We're going from left to right. No need to adjust our bounds. So from 2 to 4, we just have to look to see what area are we looking at. So we're looking at this shaded region here. This is area of 1. This is an area of 1/2. So 1.5 or 1.5. It's above the x-axis, so we're accumulating in the positive direction. Any questions?
Why is it 4 to 2 or 2 to 4?
It's 2 to 4 because of the definition here. We know we're using the g of x because that's a better fit than g prime and g double prime. And yeah, we just always just follow whatever the rule says. It could be from 3 to x, could be from x to 4. Wherever the x is, we're just going to follow what it says. Okay, next up, find g of -2. So again, we're still using the same definition. We want to go from 2 to -2. Always start off with what the rule tells you, and then after you write something down, then you can decide, okay, do I need to adjust it? Then adjust it. Don't try to do too much at one time. You may forget about the negative if you do that. Okay, so we swap the bounds. Make sure you, the bounds are out of order. So swap the bounds, pull the negative outside from -2 to 2. And these regions here. So I have, let's see, the 1/2 negative 1/2 cancels out. 0, 1 minus 1/2 is just 1/2. So I have 1/2. I got to make sure I keep that negative that is sitting out in front. So -1/2 or -0.5. Okay, any questions here? Okay, next up, find g double prime of -3.5. So let's look to see what definition we want to use. We want to use this one. So g double prime of -3.5 is f prime of -3.5. So we go to -3.5. I'm going to highlight that point there. But it's not asking for the order pair, right? It's asking for the what at this point?
Slope.
The slope, right? It's a nice straight line here. So I just have to figure out what the steepness of that line is, right? So pick any 2 points that you can easily find order pairs of and just do rise over run, up 1 over 1. This line has a steepness of 1, slope of 1. That's my f prime of -3.5. Okay, yeah.
Wait, how do you get the slope of 1?
I use these 2 points here. You can use these 2 points as well. Any 2 points that you can easily identify on the line, you can just do rise over run.
So you'd use like -2, 0, and like -3.5.
All right, next up,
1.
for what values of x is g increasing? So we're talking about increasing, decreasing for g. Remember, this is not the g function, right? This is f, but it's also what? G what? G prime, right? So this is not g of x. We can't say, okay, increasing, decreasing, increasing. We're asking about the increase, decrease of a graph that is not shown. But this is the derivative graph. We can create a sign line and get a better idea as to how the actual graph is moving. So I'm going to label what I'm looking at here. Above the x-axis is where my original g graph is going to experience positive slope. Any negative y values that I see is going to represent where the original graph is going to experience negative slope. Anything on the x-axis, slope 0. So if I create a slope sign line here, what critical points can I place onto my slope sign line? Good. X-intercepts, right? -3, 0, and 2. Right, what's happening between -4 and -3?
Negative.
Yeah, below the x-axis, right? Don't look at how the graph is moving. Look at where it's located. So here, below the x-axis, so negative. Between -3 and 0, positive, it's above the x-axis. Between 0 and 2, below the x-axis. And then between 2 and 4, above. So look at the arrows here. The arrow is actually showing us how the actual graph is moving. Okay, so falls, rises, falls, rises. Okay, so where's the graph increasing? Increasing in these two intervals. Okay. Now for G, it says for what values of F is G prime decreasing? Okay, so this is more straightforward because this is the G prime graph. Okay, so now we can just look at what this graph is doing. So where is this G prime graph actually decreasing? Yeah, between -1 and 1. Okay. So this is the decreasing of G prime is basically telling us the concavity, okay, the concavity of the G of X graph. Or they could have said, for what values of G is G of X showing concave down? So concave down would be this, which is the same thing as G prime decreasing. Okay, find absolute extrema. Okay, where do we, okay, so again, what theorem is this asking us to apply here? EPT. So if we want to do extreme value theorem, what candidates do we have to consider? Okay, endpoints, critical points. Where do we pick this off of? The slope sign line or the concavity sign line? Slope sign line. All right, so we have our G prime sign line. Are we going to use all these points here? Okay, but are all these critical points relative max and relative mins? Yes, okay, there's a change in sign in each of these, right? There's a relative min here, that could be a potential absolute minimum. There's a relative max here, that could be a potential absolute maximum. There's a relative min here, could be absolute minimum. And then the endpoints, -4 and 4. So we have to test all these, all 5 points. Okay, so I'll start at the, oh, sorry, my bad. It's only between what? It's only between -1 and 3. Sorry. So -1 is our endpoint. It's not showing up on the table, but it's an endpoint for us. So we'll test -1 and 3, and where else? 0 and 2. Okay, so we have a few less points. Just 0, 2, -1, and 3. Okay, so we go back to our definition, right? Our definition is going to tell us what each of the order pairs are. All right, so I'm looking at this. The bounds feel out of order. I'm going to swap the bounds and pull a negative outside. Okay, so -1 to 2. I have 1/2, -1/2, that cancels out. -1/2 is -5 with a negative outside already. So -1/2, which is 1/2. Okay, 3 more points to go. Any questions so far?
Sorry, I'm just going back, but like, why'd you do G double prime up there? For G instead
yeah,
of, like
uh,
at the end? Like, how come it wouldn't just be because G prime is less than?
We can. There's multiple ways of doing this. I just want to just show that this is related to concavity. So anything that is positive or negative slope is telling us about concavity of the original graph.
Does it matter what like?
You can also say because
Just do like because G.
I mean, then we're saying the same thing. G prime is decreasing because G prime is decreasing. Right. So we want to just give it a different. Yeah. Okay, G of 0. Okay, the bounds are out of order. Okay, so 0 to 2. It's -1, right? With a negative outside. All right, next up, G of 2. What's nice about this one?
It's equal here.
Yeah. Whenever the bounds are the same, I know it's going to zero out. There's no work to do there. That makes it nice. Next up, G of 3. Okay, 2 to 3, what do we see? Just 1/2, right? No adjusting the bounds. Everything looks pretty good here. Right, so I have 4 candidates here. I'm going to compare these 4 numbers. What's the highest number that you see? That's your absolute max value. Lowest number you see is that's your absolute min. Okay. Okay, next up. The following table shows the size of an incoming wave headed towards shore at a given moment. This is the distance from the left of the wave, and then you have the height of the wave. It says use trapezoidal sum with 6 subintervals to indicate data in the table to approximate the area of the face of the wave. So essentially, we know we're going to take the antiderivative, or we're going to take the integral, or approximate the integral of this. Right. So we're doing the integral from 0 to 53 of h of x dx. It's quickly lined because it's an approximation. Now let's talk about something here. H of x is in terms of what? Feet. Dx is the x value. It's also in terms of what? feet. What are we going to do to get to our new units of measure? Multiply, right? It's h of x times d of x. So what is our new unit going to be after everything's said and done? Feet squared. I know that we see feet. I know we're going to want to say answer in terms of feet, but just keep in mind, anytime there's integral here, something is changing. Your units are changing. You're multiplying two things together, or you're involving area of some sort. If I find the area of something, the units are changing, right? Because I'm multiplying the units together and multiplying values together. Okay. Okay, so we'll come back to that. All right, 6 trapezoids. So this is my first subinterval, second, third, fourth, fifth, sixth. Yeah, up here next to the tissue box. It's also in your packet, but we're doing the last page of our packet. Okay, so trapezoid, our area is 1/2 width, height 1 plus height 2. All the widths, we just subtract the x's here. And then add the heights. Okay, as long as you have those numbers in place, I'll just tell you what that is so you don't have to spend all that time entering your calculator. Part B, estimates the definite integral from 0 to 53 of h of x dx using 3 middle rectangles. Okay, so 3 middle rectangles here. I'm going to see if I can space this out here. Well, every 3. (18 minus 0), that's a width of 18. I want to pick that middle height. 36 minus 18. And then 53 minus 36, 17. So there's my dimensions for my middle, my 3 rectangles. Width of 18, height of 5, width of 18, height of 26, width of 17, height of 7. Yes, I will. Yeah, I'm looking for correct units.
Why is this a Fox name though? And why is it not exact?
Because we don't have the actual curve. we're not doing the actual integral. So, you know, there's a lot of missing space in between. So, you know, anytime we're using geometric shapes of a graph that's a curve, we know it's just an approximation, right? Whether it's a rectangle or trapezoid, those are always gonna be approximations. Yeah. No, it's fine. But it is nice to understand that this isn't the exact value. We would have to have some more information about, you know, the curve of the graph. But yeah, just understand that anytime we do Riemann sums, it's always an approximation of the actual graph, of the actual area, unless it's a geometric shape. Okay. All right. Find the average height on the interval. So average height, that's average value theorem. Let me write out average value theorem.
Can I just put 1/53 times 677? What do you want me to have to show the?
I want to see the integral notation so that I know what you're pulling from, what you're using. So we know we can replace that with an approximation that we found from part B. And then, so we have feet squared. We're dividing by feet. So our average height will be in terms of feet. Those students were asking, wait, why? Okay, so let me show the work first. So some students have asked about, you know, if we're taking the depth integral and it's feet squared, how come it turns into feet? And the reason why is because that's true, that 677 is in terms of feet squared, but then we're dividing by the width, right? So we're dividing by 53 feet, and then that's going to take us back to where we started. Feet squared divided by feet is feet.
So this kind of problem with the table is gonna like look pretty much like this one.
It's going to be more like the one that we did yesterday with interpreting. So we'll do another one of those.
It's like you have to write them, interview a question, interpret the meeting.
Right, interpret, right. Like, what does this represent? And so just understand that if something is, if you're starting with ounces per minute or feet per second, what you're doing is, if you take the integral, you're figuring out how much you're gaining, right? Either if it's ounces, then that's how much water has been added to the cup, or if it's feet, then that's how much distance you've traveled. So, but we'll look at some of those examples.
Can that be negative? Like
Yes, your displacement can be negative if you're traveling backwards, right? But yeah, but if something is like, if water is being added to the cup, then it's always going to be water added.
It's not.
Mm-hmm. Yeah, we're gonna worry about something like that. Okay, so let's look at page 8. Any questions so far here? Okay, well, why don't we do this? Why don't we, I know we did page 11, but let me just run through what we did there. Hopefully it's fresh in your mind, but
Those 11 with the particle motion is going to look like.
right. Your particle motion will look like, we spent class period doing that. So let me just go through those steps again so that you, if you have any questions, I can answer them. Let me find this sheet with, okay, here it is. Sure. Yeah. Let me get to that first. Okay. So first we sketched our graph, right? And we know how to create our sign line because we know that x-intercepts will be your critical points on your velocity function. And then above and below is going to be whether you have positive or negative velocity. And then you know the peaks and valleys, the hills and valleys of your velocity graph will be your points of inflection. So you're going to do your second zero or second trace max and min feature to help you find your critical points. And then you look at the slope, right? Positive slope is concave up, negative slope is concave down, positive slope is concave up. Or in other words, positive slope is positive velocity, positive acceleration, negative acceleration, positive acceleration. Are we good with the graphing and finding all that? Okay. Part B, find the time when the object is motionless. So we just picked out where velocity is equal to 0, 0, 3, and 9. Okay, good there. Find velocity. So we do, and we use f an integral, second alpha trace, plug 4 into the velocity function, and we got a number, and our velocity is inches per second, or pay attention to your units. Could change, could be feet per minute. It could be kilometers per hour, right? Always pay attention to whatever they define as your units and use those. Find acceleration. This is your n derivative feature. So math 8 n derivative, plug 4 into the to have it evaluate the derivative of velocity and plug in the 4 to get your acceleration. And your units of measure is, in this case, inches per second squared. It could be meters per hour squared. It could be kilometers per per day squared, right? So something in that form. Is the object's speed increasing or decreasing? So here we got to do what? Compare
The signs.
velocity and acceleration, right? Same signs would be increasing speed. Opposite signs would be decreasing speed. Now, let me change the question up a bit. What if I said, is the object's velocity increasing or decreasing? What would you look at? Okay, what are you looking at though?
C.
I know you want to because you see the word velocity, but is the object's velocity increasing or decreasing? It's not saying is the velocity positive or negative. It's saying is the velocity increasing or decreasing? This is not really talking about velocity. It's talking about what? Acceleration. Right. I know it's kind of tricky there. Velocity increasing is asking about the rate of change of velocity. So that's acceleration.
So then you look at the acceleration.
Well, yeah, either acceleration sign line, or you can just look at it from here. Because it's negative, right? We don't compare signs if it's velocity increasing or decreasing. If the speed increasing, decreasing, then we compare signs. Next up, total displacement. So total displacement is the definite integral from A to B of velocity function. I'm looking for the integral notation as well as your answer. Math 9. Next up, find the total distance. Total distance is similar to total displacement, but your absolute value is around v of t. So I want to show you a couple of incorrect notations that you're not doing here. For total distance, or I'll put it on that. So people online can see. Okay, so total distance notation looks like this. This is correct. Okay. These are not correct. Okay, that's not correct. That's also not correct. Okay, everybody okay with notation here? Okay. So you're going to use the math number ABS, the absolute value feature. I'll leave that up on the board there. And it's okay to have displacement being negative, but your total distance should always come out to be positive, right? Because every forward and backward movement, it's calculating them as all positive values. Next up, given x of 0 equals 3, find x of 11. So basically, this is saying that if I'm starting at location 3, where am I going to end up when time has passed to 11 seconds? Like where, because this object is moving along the x-axis, right? So it just wants to know where is it going to end up on the x-axis at 11. So we're just looking for a location. So this is not different from this, right? These two, it only cares about how much progress it's made. It doesn't care about where it's actually located. Part J is actually asking about location. So if I'm looking for location, I want to use this formula. Final position equals initial position plus displacement. So this case, x of 11 is what we're looking for. We're looking for the object's location at 11 seconds. We're given the object's location at 0 seconds. And then we're trying to figure out how much progress does it make in the 11 seconds that passes. So x of 11 equals, okay, we're given this, right? X of 0 equals what?
3.
3. And then this is calculator work, right? Displacement gives us negative 7.993 or negative 10.99.
So do you want us to write out the formula of the test? Or?
Yes, I want to see your integral notation. Okay. So x of 11 equals. And let me give you one more variation of this, okay? Find x of 3 given that x of 8 is equal to 4. Okay, so I'm looking for x of 3, so that's going to go here, right? What am I given? X of 8. Okay, where am I starting and where am I ending? What's my starting t-value? 8. And I'm ending where?
3.
3. Hmm? Because that's what's given to us, right? They're telling me that this object is located at 4 on the x-axis, and it's asking, backtracking here, at 3 seconds, where is it located? Now, this feels backwards, but is this going to be a problem for the calculator? I would say you can switch the bounds, but the calculator can handle this for you. Right? It's not like we're reading a graph and we're trying to figure out positive, negative. So that's fine. If you want to change it, you can, but the calculator can handle this for you. But if you do want to change it, then you do have to make sure you pull the negative in front. It's just additional step, but if you feel more comfortable with this, you're more than welcome to do that. I'm sorry? That's right. That's your final position. That's That's always what you're looking for. That's the unknown.
So for that one, would you do math?
I'll do math 9
Math nine.
because that's that definite integral. Right? Math 8 will be derivative. You guys get 24.785. Okay. Now, I do want to point out something that students do make a mistake with this is sometimes students want to write it this way. Students would say, oh, okay, x of 3 is equal to x of 8. Okay, I want to go from smaller to larger, so they do this. And what's wrong with this? Yeah, I know we're going from smaller to larger, but we're not. We have to follow what the formula says, right? The formula says the A needs to match with your initial, and your B needs to match with the final. And if you swap the bounds without taking into account, then your sign is off. And you can always make it the correct order, but then you have to make an adjustment with your signs. Does that make sense? Sure. This is A.
Okay.
So think of it this way. I'm starting here and I'm ending here. That's your starting point, that's your ending point. So just make sure that these numbers match and then these numbers match. You can swap it, but swap it after you get the definition down. But both of these are correct. Calc can handle this. The Calc can also handle this. What's the negative?
And would you not put it in like inches? It would have a unit?
Yeah, position wouldn't have, you, I'll say this, with position, I'll accept either.
Okay. Just-
But displacement and distance does need units.
Okay.
Okay, oh, and then the last part is average value theorem. Average velocity is the area divided by the width. So this is in terms of inches. We divide by 11, which is seconds. So average velocity, we're back to inches per second. Okay, page 9, is it? Or step 8 for page 8.
Is there a question on the test also? There's only 3 type of question.
No. It'll be like page 7 and 8, kind of.
And then one of these.
Right. Okay, let's look at, this is the one that is asking about Joanna jog. Joanna jogs along the straight path between 0 and 40 minutes. Joanna's velocity is given by differential functions. Select values of v of t, which is measured in minutes, and v of t. So she's jogging along a straight path, right? So she's either stopping, moving forwards, or moving backwards. So let's just visualize what's going on. So at t equals 0 minutes, she hasn't started running yet. 12 minutes in, she's running at 200 meters per minute. 12 minutes in, 20 minutes in, she's running at 240 meters per minute. 24 minutes in, she's running at negative 220 meters per minute. What's happening here?
She going backwards.
She's going back, right? She's backtracking, you know. And then 40 minutes, she's back on going forwards again. So it doesn't mean that this is the only place that she's going back, but this is at this. But we just have what we have, right? We just have this limited amount of data. We know at the very least she's moving forwards and moving backwards and moving forwards again. In terms of the meaning of v prime of 20. So v prime of 20. First off, what is the unit going to be? Yeah, it's going to be meters per minute, right? You know that if I want to get from velocity to acceleration, I'm asking for the rate of change of velocity, which units will change. Okay. So v prime of 20 is the acceleration at 20, which is the rate of change of velocity. The rate at which what?
Johnson.
Then that's just velocity, right? You want to say the rate of change of velocity, basically. Yeah, I want a bit more, right? It's like acceleration, but what does acceleration mean, right? Use the words rates of change to indicate that we understand what that means. Yeah, it's not asking us to find it. It'll ask us to find it for part B. Define it, that's right, define it, yeah. So what that means is, at 20, this is indicating that, acceleration means that she's speeding up or slowing down, right? In this case, we expect probably her to be speeding up if we're pulling those two values. Okay, approximate v prime of 18. So want to approximate what is her acceleration between at 18. The best we can do is pick these 2 points and find the what between these 2 points. Slope.
So is acceleration always going to be minutes squared?
It's always velocity divided by time. So it could be meter per minute squared. It could be kilometers per hour squared.
Velocity is always just like minutes.
That's right. It's distance divided by time.
Page 7, when it's like water,
Mhm.
would you still say like the rate of change of velocity?
You want to use velocity there. You would say that the rate of change of water added is increasing, or the rate of change of water added is decreasing.
So you only use velocity when it's like
When there's motion involved, right? We don't want to do velocity, right? Velocity acceleration doesn't fit when we're talking about water being added into a cup, right? Okay, next up, interpret the meaning of the definite integral from 20 to 40 of v of t dt. What's going to happen after we go through this process? It's going to turn into what? It's not going to stay velocity, right? This is meters per second. Yeah, position or change in distance, right? Change in distance. So I want to kind of show you what that means here. If I apply first theorem, we know velocity turns into position, right? So it's x of 40 minus x of 20. This is going to be where he's located 40 minutes, where she's located 40 minutes versus where she's located 20 minutes. And if I do x of 40 minus x of 20, that indicates how much distance she's covered in those 20 minutes, right? The change in distance. You don't have to show the formula, but I just want to prove to you why it's a change in distance, right? Because if we know where she's located at 20 minutes versus where she's located at 40 minutes, if we subtract those two, then that's going to tell us how much she's traveled in between those 20 minutes. It's a change in distance. Right, we don't want to say
Can you
change in
also say the
velocity,
change
even though
in velocity?
you may be tempted to do that because you see something that is something in terms of velocity, but things have changed, right? This is in terms of distance now. We're accumulating her velocity. So if we accumulate her velocity, then we know exactly how much she's traveled. Okay, so that's the hard part. After that is just using geometric shapes to approximate the distance traveled. Now, between 20 and 40, this is my approximation. I got negative 520 meters. So what does that mean? Can you phrase this so that it makes sense in terms of what's going on? Okay, she ran backwards, but can you be more specific? Like, what does that mean?
Between
Uh-huh.
20 and 40, she.
Okay. Okay, how about this? Between 20 and 40 minutes, she ends up 520 meters to the left of where she started. Does that make sense? Right. So between 20 and 40 minutes, she's going to end up this distance to the left of where she was at 20 minutes.
You should write out the sentence. Right?
I'm sorry?
You have to write out that sentence, right?
No, but I think, well, if I ask you to interpret what this means, then I would ask you, yeah.
Could you say that?
Yeah, so here, this means, so Joanna ends up 520 meters to the left of where she started if we are comparing between where she was 20 minutes versus where she is 40 minutes, at 40 minutes. So in that 20-minute period. Okay, approximate Joanna's average velocity using part D. So we use average value theorem. We know that she covers 520 meters to the left, going left. But if we divide that over 20, then we can space it out and say, okay, that means she's roughly gaining 26 meters to the left per minute. She's traveling negative 26 meters per minute in that time period. I'm sorry?
Average velocity.
Yes, average velocity is negative.
These are the questions. These one derivative will always be this time equals to fx.
Yeah.
Always.
Oh, so, right, so, do you have a overview? I think I got it, but do you want to do alpha trace?
I believe in you. I appreciate it.
Oh, so you.
I do. Like the man.
And then when you're trying to find the derivative that you the slope,
That's right.
and you look at that.
This one is
Just
just,
their thing.
because H prime of 3 is F of 3.
Here it is, or whatever. Oh, yeah. I forgot
Oh,
about
which one?
Yeah, this one is because it's asking for F prime of 9.
Watch this.
So that's the slope.
So -2. Okay.
Well, the slope of this line segment is,
Y1 minus Y2.
that's right, yeah, or you can just count, you can go up 1 over 2, so that's,
Oh,
or sorry, up 2 over 2, that's possible.
okay, thank you.
All right, see.
Written.
Okay, no, exactly.
They were like, when I have like, four.
You have to try it.
So this, could you say like the rate of change of the water instead of like, is the rate of change,
This is the rate of change.
but it's only does one.
It's- Right,
But if I say rate of change, like, is it,
well, we'll say that the rate of the water added is increasing. So I'm looking for those words, rate and increase, or rate from change, or rate of decrease. Because it's a rate of a rate, right? So
what's the rate of velocity?
is changing, which is acceleration. Hey guys, I need all your book bags.
Like this, it's like, you have to explain this, it's like how fast the rate of the water is added, but if you're like,
Not with velocity.
but if you're moving, then it's like the rate of velocity is changing.
How fast the rate of water is.
So velocity, I just plugged in.
Like water's increasing.
I feel like that's
This is map 8. This is map 8 into it. First figure out now. So you see how this was ounce per minute, but now it's going to turn into an ounce per minute. We're accumulating these rates here. So now everything that is here is in terms of there's balancing, right? So basically this counts how much water has been added because all the weights have now been accumulated. Like here, instead of in terms of meters. Guys, for number 2, you guys circle E, F, and G. I forgot to include additional instructions. Include your integral notation for your work. Circle it and just write integral notation needed. Very good. For 2, E, F, and G.